Welcome to Sleeping Researcher, a channel dedicated to gentle science narration, designed to help you relax and drift peacefully into sleep. Here, we explore the wonders of the universe in a calm and soothing voice, guiding your mind toward rest while satisfying your curiosity. Today, we will embark on a quiet journey through one of the most fascinating and mysterious aspects of our reality: time. Time is something we all experience, yet it remains elusive and deeply complex. From the steady ticking of a clock to the grand scale of cosmic history, time shapes everything around us. But have you ever wondered what time really is? Or why, despite all our imagination and stories, we cannot travel back to moments that have already passed? In this narration, we will gently explore how time works according to modern science, touching on ideas from physics and philosophy, and why the flow of time appears to move only forward. We will consider the nature of cause and effect, the arrow of time, and the limits that the laws of the universe impose on time travel. If you find this journey through time intriguing and relaxing, please take a moment to like this video and subscribe to Sleeping Researcher. Your support helps us continue creating soothing science stories that calm your mind and feed your wonder. Now, let us begin our peaceful exploration of time itself and why the past remains a place we can only visit in memory. Imagine a river flowing gently through a quiet valley. Its waters moving steadily onward, never reversing course. This river is much like time itself, a continuous, unidirectional flow that carries everything from the past into the present and onward into the future. Time is an ever-present dimension in which all events occur, shaping our experience of reality. It connects moments, memories, and possibilities in a seamless procession, allowing us to perceive change and causality. Understanding time is fundamental to grasping our reality and why we experience it the way we do. Time, as we perceive it, is deeply intertwined with the laws of physics and the structure of the universe. According to Einstein's theory of relativity, time is not an absolute entity flowing uniformly everywhere. Instead, it can stretch and contract depending on relative speed and the influence of gravity. This means that time is flexible in a sense, yet it remains bound to the fabric of space-time, a four-dimensional continuum where space and time coexist. Despite this flexibility, time always moves forward for us, tethered to cause and effect. Events unfold in a sequence that cannot be reversed, preserving the direction we call the arrow of time. The impossibility of traveling backward in time arises from this fundamental asymmetry in the laws of nature. While some equations in physics work equally well forwards or backwards, the macroscopic world we inhabit is governed by entropy, the tendency for systems to move from order to disorder. This principle, articulated in the second law of thermodynamics, gives time its unmistakable direction. As entropy increases, the past becomes fixed and irreversible. We remember what has happened, but cannot undo it. This irreversible flow is why we cannot revisit moments, recreate past experiences, or alter what has already transpired. Time's arrow points only forward, guiding the unfolding of reality. Our experience of time is also shaped by consciousness and memory. We perceive time as a continuous stream because our minds integrate sensory information into a coherent sequence. Memories anchor us to the past, while anticipation draws us toward the future. However, these mental constructs do not alter the physical nature of time. They simply color our perception of its passage. In this way, time is both a universal dimension and a deeply personal experience. Our awareness of time's flow influences how we live, learn, and grow, even as the universe itself marches steadily onward through the temporal landscape. Exploring the nature of time reveals profound connections between physics, philosophy, and human experience. While we cannot move backward through time, our understanding of it continues to evolve, inviting new perspectives on the universe and our place within it. This journey into the essence of time deepens our appreciation for the present moment and the unfolding future. With these insights, we can begin to explore how time influences not only the cosmos, but also the intricate patterns of life itself. Time is often described as a river that flows endlessly from the past through the present and into the future. Yet unlike rivers that we can see, touch, or measure by their physical properties, time is intangible and invisible. Physicists understand time as a dimension, similar in some respects to the 3 dimensions of space, that allows us to order events and perceive change. This dimension is essential for describing the universe, enabling us to distinguish between what has happened, what is happening, and what will happen. We measure time through cycles, such as the rotation of the Earth or the vibrations of atoms in a clock, creating units like seconds, minutes, and hours. These measurements help us synchronize daily life and scientific experiments alike. However, time itself is more than just these units. It is the framework within which all events are organized, a continuous and universal backdrop against which the story of existence unfolds. From the perspective of classical physics, time flows uniformly and inexorably forward, independent of the observer. Sir Isaac Newton imagined time as absolute, a constant river flowing at the same rate everywhere, unaffected by anything within the universe. However, this view was revolutionized in the early 20th century when Albert Einstein introduced his theory of relativity. Einstein showed that time is not a fixed entity, but is relative and intertwined with space itself, forming a 4-dimensional fabric known as space-time. According to this theory, the passage of time can vary depending on factors like velocity and gravitational fields. For example, time slows down near massive objects or at speeds approaching that of light. This phenomenon, known as time dilation, has been experimentally confirmed and challenges our everyday intuition about time's uniformity. Even so, despite these complexities, time continues to move forward, never retreating. The question of why we cannot go back in time touches upon the fundamental nature of causality, the principle that cause precedes effect. Our experience of time is deeply rooted in this cause and effect relationship, shaping the arrow of time that points from past to future. The second law of thermodynamics, which governs the increase of entropy or disorder, offers a physical basis for this directionality. Entropy tends to increase in an isolated system, meaning processes naturally evolve toward more disordered states. This growth in entropy gives time its irreversible character, making backward travel through time seemingly impossible. While some speculative theories and solutions in physics suggest the possibility of time loops or wormholes, these remain hypothetical and fraught with paradoxes. Thus, the forward flow of time remains a fundamental aspect of our reality, grounding the sequence of events and preserving the logical order of the universe. Beyond physics, time also carries profound philosophical and experiential dimensions. Our consciousness perceives time as a continuous unfolding where memories anchor us to the past and anticipation draws us toward the future. Yet, the present moment, ever fleeting and elusive, is where life truly happens. The impossibility of returning to the past highlights the preciousness of now, encouraging mindfulness and presence. In some interpretations, time may be seen as an emergent property of the universe, arising from more fundamental processes that are not yet fully understood. This perspective invites ongoing inquiry into the nature of reality itself, suggesting that time might be more fluid or layered than our everyday experience reveals. As science progresses, it continues to challenge and refine our understanding of time, opening new pathways for exploration. By exploring time as a measurable dimension and recognizing its intricate connections to space, entropy, and consciousness, we gain deeper insights into why time moves only forward. This understanding shapes not only physics but also how we experience life and the universe. As we continue to investigate the mysteries of time, we prepare ourselves to delve into its influence on the cosmos and the fabric of existence itself. With these reflections, we now turn toward examining how time interplays with the vast structures and dynamics of the universe. In physics, time is not merely a fleeting sensation or a sequence of moments slipping away. Instead, it is treated as a fundamental coordinate, much like the dimensions of space. This perspective arises from the framework of spacetime, introduced by Einstein's theory of relativity, where time and space are intertwined into a single four-dimensional continuum. By conceptualizing time as a coordinate, physicists can describe events with precise positions, not only in space, but also in time. This allows for a richer understanding of how objects move and interact, and how cause and effect unfold within the universe. Time's role as a coordinate also means it can be measured, quantified, and incorporated into the equations that govern physical laws. However, unlike spatial dimensions, time exhibits a unique asymmetry, a direction often called the arrow of time, which gives it a distinct flow from past to future, a feature that remains a profound subject of inquiry. The flow of time, as seen through the lens of physics, is deeply connected to the concept of entropy, or the measure of disorder within a system. According to the second law of thermodynamics, entropy tends to increase over time in an isolated system, providing a natural directionality to time itself. This means that while the fundamental laws of physics are largely time-symmetric, operating the same forwards and backwards, the increase in entropy creates an irreversible progression. This irreversible change is why we experience time as moving forward, and why phenomena such as broken eggs or mixing fluids cannot spontaneously reverse. In this way, entropy links the microscopic world of particles and energy to the macroscopic experience of time's arrow, grounding the flow of time in physical processes that govern the universe. Despite the elegant mathematical description of time as a coordinate, the notion of traveling back in time remains elusive and, according to current physics, impossible. Time differs from space in a crucial way. While we can move freely in three-dimensional space, our movement through time is constrained. The structure of space-time, as understood through relativity, allows for certain exotic solutions known as closed, time-like curves, which theoretically could permit time loops. Yet, these solutions require conditions such as negative energy or exotic matter that are not known to exist or be stable in our universe. Furthermore, causality, the principle that cause precedes effect, is a cornerstone of physical laws, and violating it by traveling backward in time would introduce paradoxes that challenge our understanding of reality itself. These constraints suggest that while time is a coordinate, it has an inherent direction and stability that prevent us from reversing its flow in any meaningful way. The nature of time as a dimension also invites contemplation about how it relates to our conscious experience. While physics treats time as a parameter within equations, our perception of time's passage is deeply tied to memory, awareness, and change. Biological processes, neural activity, and the flow of information all contribute to the sensation of moving from past through present toward future. This subjective experience aligns with the physical arrow of time, but also highlights the complexity of time as both a physical and experiential phenomenon. While physics provides the framework to measure and predict time's behavior, the full picture requires bridging these objective models with the lived reality of time's flow, a challenge that continues to inspire interdisciplinary exploration. As we seek to understand time more deeply, physics guides us through a landscape where time is intimately woven with space, matter, and energy. It is a dimension that orders the cosmos, allowing events to be mapped and experienced, yet it resists reversal, preserving the sequence of cause and effect. These insights set the stage for exploring time's role in the grand cosmic structures and the dynamic evolution of the universe. With these ideas in mind, we now prepare to examine how time shapes the vastness of the cosmos and influences its unfolding story. Time, as we perceive it, flows in a single direction, an experience that feels both natural and inevitable. This unidirectional flow is often described as the arrow of time, a concept introduced to capture the essence of why moments pass from past to future, never the reverse. At the heart of this phenomenon lies the second law of thermodynamics, a fundamental principle in physics stating that entropy, or disorder, tends to increase in an isolated system. In simpler terms, systems evolve from states of order to disorder, which imparts a directionality to time itself. When we watch a glass shatter or a candle burn, we see processes that move forward with increasing entropy. And this irreversible progression is what anchors our sense of past and future. Although the fundamental laws governing particles and forces are mostly time-symmetric, meaning they work the same forwards and backwards, the macroscopic world we inhabit follows a clear temporal direction because of this relentless climb in entropy. This delicate interplay between microscopic reversibility and macroscopic irreversibility forms the backdrop against which time's arrow is painted. Another perspective on the arrow of time emerges when we consider causality, the principle that causes precede effects. This ordering is essential for maintaining a coherent narrative of events, allowing us to understand sequences and relationships within the universe. If time could reverse, the cause-effect relationship would unravel, leading to paradoxes and contradictions that challenge the very foundation of logic and experience. Physical theories, including relativity, respect causality by forbidding information or matter from traveling faster than light, thus preserving the temporal order of events. Additionally, the expansion of the universe contributes to the arrow of time. As the cosmos continues to grow and evolve, it moves from a hot, dense, and highly ordered state toward increasing complexity and entropy. This cosmic progression aligns with our everyday experience of time moving forward, embedding the arrow of time into the fabric of space-time itself. While these insights deepen our understanding, they also highlight why traveling back in time remains beyond reach, as doing so would violate these fundamental principles. Beyond thermodynamics and causality, the nature of time itself presents profound challenges to the notion of reversal. In Einstein's theory of relativity, time is not absolute but interwoven with space, forming a four-dimensional continuum called spacetime. This framework allows for time dilation and other phenomena that bend our intuitive sense of time's passage, yet it does not permit simple backward travel to earlier moments. The equations of general relativity allow for unusual solutions known as closed time-like curves, which theoretically loop back in time, but these require exotic conditions such as negative energy or hypothetical constructs like wormholes. Such scenarios remain speculative and have not been observed in reality. The stability of causality and the thermodynamic arrow of time impose stringent constraints, ensuring that macroscopic time travel remains a concept of science fiction rather than scientific fact. In this way, the universe protects its temporal order, preserving the delicate balance that allows cause and effect to unfold harmoniously. On a more philosophical level, our experience of time is deeply rooted in memory and consciousness, which reinforce the forward flow of time. We remember the past, but not the future, anchoring our sense of self and narrative in a temporal direction aligned with entropy and causality. This psychological arrow of time complements the physical arrows, creating a unified experience of moving forward through moments. The asymmetry of time is thus not only a physical reality, but also a cognitive one, shaping how we perceive reality and our place within it. Attempts to reverse time would challenge this fundamental aspect of experience, destabilizing the continuity that defines existence. As science continues to explore these mysteries, it becomes clear that the forward march of time is woven into the very fabric of the cosmos and consciousness alike. The arrow of time guides not only matter and energy, but also our understanding and interpretation of the universe. Understanding why time flows forward rather than backward opens a window into some of the deepest questions of physics and existence. It draws together threads from thermodynamics, relativity, cosmology, and the nature of consciousness, revealing a complex tapestry in which temporal directionality is fundamental. While our current knowledge prohibits backward travel through time, the pursuit of these questions continues to inspire curiosity and wonder, pushing the boundaries of science and philosophy. As we prepare to explore time's influence on the vast cosmic structures and the evolving universe, we carry with us the profound insight that the arrow of time is not just a feature of clocks and calendars, but a cornerstone of reality itself. This understanding paves the way for deeper inquiry into time's role in shaping the cosmos and our experience within it. The concept of entropy, central to the second law of thermodynamics, provides a profound explanation for the unidirectional flow of time. Entropy can be understood as a measure of disorder or randomness within a system, and the second law states that in an isolated system, entropy tends to increase over time. This irreversible increase in disorder gives rise to what is often called the arrow of time, a guiding principle that ensures time moves forward rather than backward. While physical laws at the microscopic level, such as those governing fundamental particles, are largely time-symmetric, the macroscopic world we observe is dominated by this gradual march towards greater entropy. This asymmetry is why we remember the past but not the future, why eggs break but do not spontaneously reassemble, and why the heat flows from hot objects to cold ones rather than the reverse. These everyday examples illustrate how entropy grounds the abstract concept of time's direction in tangible physical reality. Delving deeper into entropy reveals an intimate connection between thermodynamics and the flow of time, one that transcends simple observation and enters the realm of fundamental physics. As systems evolve, the microscopic arrangements of particles become increasingly disordered, making the reversal of these processes extraordinarily improbable. It is not that reversing time violates physical law outright, but rather that the likelihood of spontaneously decreasing entropy in a closed system is so low that it effectively never occurs. This statistical improbability imposes a practical limitation on time travel to the past, as doing so would require a local decrease in entropy, contradicting the natural progression dictated by the second law. Thus, entropy does not merely describe disorder, but actively shapes the temporal landscape, anchoring our experience of time's relentless forward momentum in the behavior of matter and energy. The insight provided by entropy also extends to cosmological scales, where the universe itself can be viewed as a vast thermodynamic system, evolving from a state of remarkably low entropy near the Big Bang toward ever-increasing disorder. This grand perspective suggests that the arrow of time is woven into the very fabric of cosmic history. The initial conditions of the universe set a direction for entropy to grow, and consequently for time to unfold irreversibly. Although theoretical physics allows for time-symmetric equations, the The boundary conditions of the universe break this symmetry, giving rise to the temporal direction we observe. This understanding ties the flow of time to the universe's evolution, linking the microscopic laws of thermodynamics to the vastness of space and the complexity of cosmic phenomena. While entropy clarifies why time moves forward, it also highlights why returning to a previous moment in time remains an impossibility within our current understanding of physics. Any attempt to reverse time would require a decrease in entropy that defies the overwhelming statistical tendencies of physical systems. This is not merely a limitation of technology or imagination, but a fundamental property of reality as described by thermodynamics. The irreversible growth of entropy ensures that the past remains fixed and inaccessible, while the future unfolds with increasing disorder. In this way, entropy anchors the abstract flow of time in the physical world, creating a boundary that confines us to one temporal direction and shapes our very experience of change and causality. This grounding of time's directionality in entropy invites us to consider time not as a mere backdrop for events, but as an emergent property arising from the fundamental laws governing matter and energy. It opens pathways to explore how thermodynamics intersects with quantum theory and gravity, pushing the frontiers of scientific inquiry. The interplay between entropy and time challenges us to rethink our understanding of reality and the limits of possibility. As we continue to investigate the nature of time, entropy remains a guiding principle, illuminating why the past is a realm of memory and the future a landscape of unfolding potential, forever beyond our reach. Consider the simple act of brewing a cup of tea. Initially, the water is hot and the tea leaves are dry, distinct and separate. As time passes, the heat diffuses through the water, the aroma spreads, and the tea leaves release their essence. This process, while seemingly ordinary, perfectly illustrates entropy at work. The molecules in the hot water move rapidly, transferring energy to cooler parts until thermal equilibrium is reached, where the temperature is uniform throughout. In this natural progression, the system evolves from a state of order with clear temperature gradients to one of greater disorder. The hot water never spontaneously becomes hotter after cooling, nor do the tea leaves reconstitute themselves from the infused water. This everyday occurrence reflects a fundamental truth. Entropy tends to increase, guiding processes forward in time and rendering them irreversible. The arrow of time, therefore, is not just a philosophical concept, but a tangible, physical reality experienced in our daily lives. Understanding this helps us see why time travel to the past defies the very fabric of thermodynamic laws. To reverse time would mean to decrease entropy universally, an act that contradicts the natural flow of energy and matter as we observe it. Walking through a room filled with scattered papers offers another simple yet profound example of entropy. Initially, the papers might be neatly stacked, representing a low entropy, highly ordered state. Over time, without intervention, they become disorganized, scattered randomly across the floor. This transformation toward disorder is spontaneous and natural, driven by countless microscopic interactions and the statistical likelihood of disordered arrangements vastly outnumbering ordered ones. To restore the original neat stack, effort and energy input are necessary, such as picking up and rearranging the papers. This illustrates a crucial principle. While entropy in an isolated system tends to increase, living beings can locally decrease entropy by expending energy. However, this local decrease is always accompanied by a greater increase in entropy elsewhere, preserving the universal trend. The irreversible nature of such everyday processes underscores why the past remains a fixed memory and why we cannot physically revisit it. The universe's relentless march toward higher entropy ensures that while memories and records of the past exist, the physical state of past moments cannot be recreated or entered. This interplay between order, disorder, and energy expenditure underpins our experience of time's forward flow. On a broader scale, the concept of entropy extends beyond physical systems to influence biological processes. Consider aging, a gradual accumulation of molecular and cellular changes that drive organisms from youthful order toward eventual disorder and decay. This natural progression is a manifestation of increasing entropy within living systems, despite their remarkable ability to maintain organization through metabolic activity. The energy organisms consume is ultimately dissipated as heat and waste, contributing to the universe's overall entropy increase. Aging reminds us that time's arrow is deeply embedded in life itself. We move forward through time as our bodies and environments reflect the irreversible transformations governed by thermodynamics. This reality imposes fundamental limits on our ability to reverse or halt time's passage. While science fiction often imagines time travel or rejuvenation, the thermodynamic truths reflected in biological aging and decay emphasize the constraints imposed by entropy. These constraints shape not only our physical existence, but also our understanding of time as a one-way journey. Even in the realm of technology, entropy plays a decisive role. Devices that store and process information, such as computers and memory systems, operate under the influence of thermodynamic laws. When data is erased or overwritten, the process involves increasing entropy in the system's environment, often manifesting as heat dissipation. This principle is formalized in Landauer's principle, which connects information theory with physical thermodynamics, asserting that erasing one bit of information necessarily increases entropy. This link between information and entropy reveals why time appears unidirectional, not only in physical systems, but also in the logic of computation and memory. Our digital records, like memories, are snapshots of the past, preserved through energetic costs. Yet it is impossible for these records to reconstruct past states perfectly or to reverse the flow of time in reality. Entropy's persistent increase ensures that information and energy transformations move forward, solidifying the arrow of time in both physical and informational domains. As we recognize entropy's pervasive influence, we deepen our appreciation for the subtle mechanisms that make time's forward march an inescapable aspect of existence. Reflecting on these varied manifestations of entropy, from the warmth of a cooling cup of tea to the aging of living organisms, and the erasure of digital data, we see a unifying theme: the irreversible transformation of order into disorder. This principle underlies why time's arrow points inexorably forward, and why returning to past moments remains beyond our reach. The increase of entropy is not merely a scientific abstraction, but a lived experience that shapes our perception of reality. It grounds the distinction between past and future, memory and anticipation, stability and change. In this light, entropy is a bridge connecting the microscopic laws of physics with the macroscopic flow of time we observe. As our understanding of entropy continues to evolve, it opens new avenues for exploring the profound relationship between time, matter, and energy, inviting us to ponder the mysteries still hidden within the cosmos. With this appreciation of entropy's role in everyday life, we are poised to explore deeper aspects of time and its enigmatic nature. As we delve deeper into the nature of time, it becomes clear that our everyday experience of its passage is just one facet of a far more complex reality. Einstein's theory of relativity revolutionized our understanding by revealing that time is not an absolute constant, but rather a flexible dimension intertwined with space itself. According to this theory, time can stretch and contract depending on the relative speed of an observer or the strength of gravitational fields. This phenomenon, known as time dilation, means that two individuals moving at different velocities or positioned in different gravitational environments can experience the flow of time at varying rates. Such effects, though imperceptible in our daily lives, have been confirmed through precise experiments involving atomic clocks flown in airplanes or placed near massive objects. This insight challenges the intuitive notion that time ticks uniformly for everyone, everywhere, and instead invites us to reconsider time as a dynamic, relative experience shaped by the fabric of space-time. The implications of time dilation stretch beyond mere curiosity. They have profound consequences for the possibility of traveling through time. While science fiction often depicts journeys back to the past, Einstein's framework sets stringent limits on such notions. In particular, the relative nature of time flows forward along what physicists call the light cone, a structure defining the sequence of cause and effect. Traveling backward in time would require moving faster than the speed of light, a feat forbidden by the laws of physics as we understand them. Moreover, the causal order, the sequence in which events influence one another, remains preserved, preventing paradoxes that would arise if the past were accessible in the same way as the future. Thus, while time dilation allows for discrepancies in experience duration, it does not open a pathway to rewind or relive moments already past. Another layer to this understanding emerges when we consider gravity's effect on time. According to general relativity, massive objects like stars and black holes warp the space-time around them, causing time to slow down in strong gravitational fields relative to regions farther away. This gravitational time dilation has been experimentally verified, for example by comparing clocks on Earth's surface with those in orbit. Near a black hole, the distortion becomes so extreme that time almost seems to stand still, relative to an outside observer. Yet, even in these extreme conditions, the directionality of time remains intact, time flows forward from the perspective of any local observer. This unidirectional flow, embedded in the structure of space-time itself, reinforces why moving backward through time is not just practically impossible, but theoretically inconsistent with the fundamental workings of the universe. The flexibility of time, then, is not a gateway to the past, but a subtle dance between motion, gravity, and the fabric of reality. As we contemplate the elasticity of time revealed by relativity, we begin to recognize that our linear experience is a product of the interplay between physical laws and the limits they impose. The universe's speed limit, the speed of light, acts as a cosmic speed bump, ensuring that cause precedes effect and that the past remains an unalterable foundation upon which the present builds. This cosmic order protects the coherence of events and preserves the integrity of our memories and histories. The absence of backward time travel in our physical theories is not a restriction born of ignorance, but a fundamental feature woven into the universe's very structure. In this way, relativity deepens the mystery of time, showing it as both relative and constrained, flexible yet irreversible. Such insights invite us to explore further, to consider how time's nature aligns with other fundamental aspects of reality. To deepen our understanding of time, it is illuminating to consider it not as a separate and independent entity, but as an integral dimension woven together with the three dimensions of space. This fusion forms what physicists call space-time, a four-dimensional fabric that underlies the universe's very structure. In this view, time is measured much like one measures distance, yet it holds unique properties that distinguish it from spatial directions. Unlike space, where movement can occur freely forward or backward, time's dimension has a clear and consistent direction, often referred to as the arrow of time. This directional flow arises from fundamental physical principles, such as entropy, which describes the gradual increase of disorder in isolated systems. Within the space-time continuum, events are located at precise coordinates, combining a point in space with a moment in time. This conceptual framework helps us to visualize how the universe evolves, not merely as a sequence of moments, but as a connected whole where time and space are inextricable. In this manner, space-time provides a language through which we can describe the cosmos with remarkable precision, revealing patterns and relationships that might otherwise remain hidden. The integration of time into space-time also clarifies why traveling backward in time remains beyond our reach. Within this four-dimensional fabric, cause and effect relationships are preserved by the structure of space-time itself. The speed of light acts as a fundamental limit, ensuring that signals or influences cannot propagate faster than this cosmic speed limit. This restriction maintains the order of events, preventing paradoxes that would arise if we could interact with the past. For example, imagine the confusion if an action could alter events that have already unfolded. Such scenarios would undermine the logical consistency of reality. Moreover, the geometric nature of space-time, as described by Einstein's theory of general relativity, shows that while it can be curved or warped by mass and energy, its overall causal structure remains intact. This prevents closed time-like curves, pathways that would loop back in time, from forming under normal conditions. Thus, the universe's design preserves a forward arrow of time, safeguarding the continuity of history and our experience of progression. The interplay between these physical laws and space-time geometry reveals why the past is fixed and the future open, guiding the unfolding of reality without contradiction. Beyond the constraints of physics, the conceptualization of time as a dimension in space-time invites us to reconsider our everyday experience. While we navigate life seemingly moving through time linearly, the space-time framework suggests that all moments, past, present, and future, exist within a vast, interconnected manifold. Yet, our conscious perception is pinned to a moving now, a present that marches steadily forward. This experience arises not from the absence of other moments, but from the way information and causality propagate through space-time. Entropy, the measure of disorder, consistently increases as time advances, providing a thermodynamic arrow that aligns with our psychological sense of time's passage. This layered understanding highlights how time's flow is both a physical phenomenon and a deeply human experience. The structure of space-time accommodates this flow while ensuring it is unidirectional, a constraint that shapes the very fabric of reality and preserves the coherence of cause and effect. In this way, time's dimensional role enriches our grasp of the cosmos, linking the vastness of space with the subtle progression of moments we live through. Central to our understanding of time is the principle of causality, the intimate link between cause and effect that governs the unfolding of events. This principle asserts that every effect is the result of a preceding cause, establishing a natural order in which events follow one another in a coherent sequence. Within the fabric of space-time, causality ensures that information and influence travel at or below the speed of light, preserving the logical structure of reality. Without this constraint, the sequence of events could become jumbled, leading to contradictions or paradoxes, where effects might precede their own causes. Such paradoxes challenge our fundamental comprehension of time and reality, raising questions about the possibility of altering the past or influencing events that have already occurred. The steadfast nature of causality acts as a safeguard, maintaining the temporal order that underlies all physical processes. It is this ordering that gives rise to what we perceive as the arrow of time, a directionality that is embedded deeply in both the laws of physics and our everyday experience. By ensuring that causes always come before their effects, causality preserves the integrity of history and the consistency of the universe's timeline. The impossibility of traveling backward in time is intimately tied to the preservation of causality. If one were to move into the past, it would open the door to altering events that have already transpired, potentially creating inconsistencies known as temporal paradoxes. One famous example is the grandfather paradox, where a traveler could prevent their own existence by changing past events, a scenario that violates causality and logical coherence. Physics, particularly through the framework of relativity and quantum mechanics suggests that such paradoxes are avoided because the universe enforces strict causal order. In relativistic terms, the light cone structure of space-time delineates which events can influence each other, restricting any backward influence that could disrupt cause and effect. Additionally, many interpretations of quantum mechanics hint at mechanisms that prevent paradoxical outcomes, such as the branching of timelines or probabilistic constraints. These safeguards imply that time travel into the past, if possible at all, would require conditions or dimensions beyond our current understanding and likely beyond the laws that govern our accessible universe. Thus, causality acts as a fundamental principle that not only orders events, but also restricts the ways we can interact with time itself. Beyond theoretical physics, the principle of causality resonates deeply with our intuitive experience of time. Our minds and memories are organized in a way that reflects the causal flow of events, anchoring us firmly in the present moment while recalling a fixed past and anticipating an open future. This psychological arrow aligns with the physical arrow of increasing entropy and the unidirectional transmission of information. It is through causality that we construct narratives, learn from experience, and build coherent understandings of the world around us. When causality is preserved, the fabric of reality remains stable and predictable, allowing complexity and life itself to emerge. The disruption of causality would not only unravel physical laws, but also undermine the continuity of consciousness and identity. In this sense, the cause and effect principle is not just a physical rule, but a cornerstone of existence, weaving together the cosmos and the conscious observer into a single, cohesive tapestry. The natural progression of cause leading to effect manifests itself across scales, from the smallest particles to the vast structure of the universe, ensuring a harmonious order that anchors time's unyielding march forward. While modern physics allows us to explore fascinating concepts such as wormholes or closed time-like curves, which theoretically could permit time loops, these ideas remain speculative and fraught with challenges related to causality. The very notion of traveling back to a previous moment raises deep questions about the consistency of physical laws and the preservation of logical order. Many physicists propose that nature employs chronology protection mechanisms, preventing paradoxes from arising and thus forbidding backward time travel in any meaningful sense. This means that while the mathematics of space-time might allow for unusual geometries, the physical universe seems to favor causal consistency above all else. Consequently, time maintains its forward direction, preserving the chain of cause and effect that underpins reality. This preservation is essential not only for the predictability of physical phenomena, but also for the coherence of the universe as a whole. It is this interplay between the possibilities hinted at by theory and the constraints imposed by causality that shapes our understanding of time's unidirectional nature. In contemplating the nature of time and the impossibility of reversing its flow, we encounter the profound role that causality plays in structuring the universe. Far from being a mere abstract concept, causality is woven into the very essence of space-time, dictating the order in which events unfold and ensuring that the tapestry of history remains intact and free from contradictions. This principle acts as a guardian of temporal coherence, forbidding the reversal of cause and effect, and thereby closing the door on backward time travel. It is through this lens that we begin to appreciate why time's arrow points only forward, why moments pass without return, and how the universe maintains its orderly progression. The cause and effect relationship thus stands as a fundamental pillar, supporting the seamless continuity we observe and experience. As we continue to explore the mysteries of time, this principle will remain central to understanding not only why we cannot go back, but also how the universe preserves its intricate balance. To delve deeper into the reasons why backward time travel remains a physical and logical impossibility, we can consider a thought experiment known as the grandfather paradox. Imagine a scenario in which a person travels back in time and inadvertently prevents their own grandfather from meeting their grandmother. This act, though seemingly simple, creates a profound logical contradiction. If the grandfather never met the grandmother, the time traveler's parent, and consequently the time traveler themselves, would never have been born. Yet, if the time traveler was never born, how could they have journeyed back to prevent the meeting in the first place? This paradox elegantly illustrates the tangled consequences that arise when cause and effect are disrupted. It is not merely a puzzle of imagination, but a reflection of the stringent consistency that the universe demands. In this way, the grandfather paradox acts as a natural safeguard against the possibility of changing the past, highlighting why the timeline must remain self-consistent and free from contradictions. The paradox underscores the essential role of causality, demonstrating that any attempt to alter past events would unravel the logical fabric of reality itself. Physicists and philosophers have long pondered the implications of such paradoxes for our understanding of time. One approach to resolving the grandfather paradox suggests that the universe might forbid any action that would create a contradiction, effectively preventing events that would alter the past in a way that negates the time traveler's existence. This idea, sometimes called the Novikov self-consistency principle, proposes that the timeline is immutable, and while we might imagine traveling to the past, our actions there would always conform to what has already occurred. In other words, events are locked into a consistent history, and attempts to change them would be thwarted by the laws of physics. Another perspective arises from interpretations of quantum mechanics, suggesting that rather than a single deterministic timeline, there could be branching realities or parallel universes where different outcomes coexist. However, these interpretations remain speculative and do not offer a practical means to reverse time in our own reality. These conceptual frameworks deepen our appreciation for the delicate balance that keeps the arrow of time moving forward, as well as the profound challenges in imagining any true reversal. Beyond logical paradoxes, the nature of time itself, as described by modern physics, provides further insight into why backward travel remains beyond reach. According to the theory of relativity, time is intertwined with space in a four-dimensional fabric called space-time, where the flow of time depends on the observer's motion and gravitational field. While relativity allows for some curious phenomena, such as time dilation, where time passes at different rates for different observers, it does not permit the kind of closed loops in time necessary for traveling into the past without violating causality. The equations of general relativity do admit theoretical solutions known as closed time-like curves, which would allow an object to return to its own past. Yet, these solutions involve extreme conditions, such as rotating black holes or exotic forms of matter with negative energy, which may not exist in our universe or could be ruled out by yet undiscovered principles. Thus, the physical laws as we understand them erect formidable barriers against reversing time. This interplay between geometry, energy, and causality reveals the profound constraints limiting our temporal journey to the forward direction alone. Moreover, the concept of entropy, the gradual increase of disorder in a closed system, offers a thermodynamic arrow of time that aligns with our everyday experience of moments passing irreversibly. Entropy ensures that processes such as aging, decay, and the mixing of substances proceed in one direction only, reinforcing the unidirectional flow of time. Attempting to reverse time would require a decrease in entropy, a feat that contradicts the second law of thermodynamics and the statistical nature of physical processes. This thermodynamic perspective complements the causal and relativistic aspects, painting a coherent picture of why the past remains fixed and unreachable. It is as if the universe itself records the accumulation of events, and this record grows ever more complex and disordered, making a return to previous states fundamentally impossible. Thus, the arrow of time emerges not only from the fabric of space-time, but also from the energetic and probabilistic tendencies inherent in the universe. In reflecting on the grandfather paradox and the broader principles that govern time's direction, we begin to see that the impossibility of traveling back into the past is deeply rooted in the logical and physical structure of reality. The universe maintains an elegant consistency by safeguarding causality, upholding the laws of physics, and embracing the thermodynamic flow of entropy. These intertwined principles ensure that time remains a one-way journey, moving steadily forward without the possibility of retracing its steps. As we continue our exploration into the nature of time, we will consider how these insights shape our understanding of existence and the mysteries that still lie ahead. The story of time is one of unfolding moments, each connected yet irretrievable, guiding us onward through the continuum of experience. Within the realm of theoretical physics, wormholes emerge as fascinating constructs, hypothetical tunnels through the fabric of space-time that could, in principle, connect distant points in the universe. These bridges, also called Einstein-Rosen bridges, arise from solutions to Einstein's field equations in general relativity, suggesting that space-time might be more flexible and interconnected than our everyday experiences imply. The concept of a wormhole invites us to imagine a shortcut, potentially allowing travel not just across vast cosmic distances, but also between different moments in time. Yet, despite their allure, wormholes remain speculative, as no experimental evidence has yet confirmed their existence. Moreover, the conditions necessary to create or stabilize such structures would require exotic forms of matter with negative energy density, substances that challenge our current understanding of physics. This delicate interplay between theory and the limits of physical reality highlights the intricate barriers that time travel must overcome. The study of wormholes serves as a reminder that while our imagination can stretch toward extraordinary possibilities, nature imposes strict rules that govern what can truly be realized.
Exploring wormholes naturally leads us to consider the implications for time travel, a subject that has captivated scientists and dreamers alike. In theory, if a wormhole's two ends were manipulated to exist at different points in time, it might allow an object or traveler to move backward or forward along the timeline. However, this notion confronts profound paradoxes and challenges rooted in causality, the principle that cause precedes effect. If one could journey into the past and alter events, it might unravel the very fabric of logical consistency, as exemplified by paradoxes like the grandfather paradox. Many physicists propose that some form of cosmic censorship or self-consistency principle prevents such contradictions, preserving the coherence of the universe's history. Furthermore, the energy requirements and stability conditions for time-traveling wormholes appear so extreme that they may be practically unattainable, if not impossible. These theoretical insights underscore the delicate balance between the mathematical possibilities within physics and the constraints that preserve the integrity of time's arrow. Even as we ponder these ideas, the universe seems to protect its timeline with subtle yet powerful laws that resist retrograde journeys. The investigation into wormholes and theoretical time travel also touches on deeper questions about the nature of space-time itself. Modern physics views time not as an isolated entity, but as intimately woven with space into a dynamic, four-dimensional continuum. Changes to this fabric, such as those implied by wormholes, would require conditions that challenge the very stability of space-time. For example, the presence of negative energy or exotic matter necessary to keep a wormhole open may lead to unpredictable effects, potentially causing the structure to collapse or produce catastrophic outcomes. Additionally, quantum theories introduce further complexity, suggesting that the quantum foam at microscopic scales could disrupt or prevent stable wormhole formation. These layers of difficulty reflect the universe's remarkable consistency in maintaining a forward-moving temporal flow. Despite the intriguing mathematical models, the physical realities seem to confine time's passage within a one-directional stream, shaped by gravity, quantum mechanics, and thermodynamics alike. As we delve deeper into these theoretical frontiers, we gain appreciation for the delicate architecture underlying our experience of time. Beyond the physics of wormholes, the study of time travel invites philosophical reflection on what it means to exist within a temporal framework. If time were malleable or reversible, our concepts of memory, identity, and causation would require profound re-evaluation. The irreversible progression of time underpins the unfolding of events and the growth of knowledge, anchoring our understanding of reality. This irreversible quality is closely tied to entropy,
the measure of disorder that invariably increases, guiding the universe toward higher states of randomness. The thermodynamic arrow of time reinforces why we perceive a past that is fixed and a future that is open. Even if wormholes or other exotic phenomena could theoretically bypass these constraints, the fundamental nature of entropy and causality appears to resist such reversals. This interplay between physics and philosophy enriches our exploration of time, revealing that its linearity is not just a practical observation, but a profound feature of existence itself. Through this lens, the universe's refusal to permit backward time travel becomes an expression of its deep, structural harmony. As we continue to examine the mysteries of time, wormholes and theoretical time travel remain emblematic of the tensions between possibility and limitation in physics. They inspire us to push the boundaries of knowledge, challenging our assumptions and inviting imaginative inquiry into realms beyond current experience. Yet, within these scientific adventures, we also confront the steadfast principles that govern reality, principles that safeguard causality and preserve the directional flow of time. The pursuit of understanding wormholes thus reflects a broader scientific journey, one that balances wonder with rigor, speculation with evidence. While the dream of moving backward through time captivates our imagination, the universe's intricate laws guide us toward a future-oriented path. As we prepare to explore further dimensions of time and existence, these reflections illuminate the profound complexity underlying the seemingly simple progression of moments. In this unfolding story, each question leads us deeper into the vast and subtle nature of reality. To consider the prospect of traveling through time is to confront some of the most profound and challenging concepts in physics. The notion of moving backward along the timeline, revisiting moments already past, evokes a powerful allure. Yet, as we delve into the mechanics of such a feat, we encounter an imposing barrier: the extraordinary amount of energy that would be required to alter the fabric of space-time itself. Theoretical models, such as those involving wormholes or closed time-like curves, suggest that to create a stable passage through time, one might need to manipulate exotic forms of energy, often described as negative or dark energy. These energies would have to counteract the immense gravitational forces that naturally tend to collapse such structures. In practical terms, the scale of energy necessary far exceeds anything humanity can currently harness or even conceive of controlling. This insight into the energy demands serves as a crucial reminder that while the laws of physics theoretically permit certain forms of time travel, the universe enforces constraints that are both rigorous and unforgiving. Understanding these energy requirements helps us appreciate why time travel, especially backward travel, remains firmly in the realm of speculation rather than achievable reality. Beyond the magnitude of energy, the stability of any hypothetical time travel conduit presents further complexities. To sustain a traversable wormhole or other time-altering configuration, it is not enough simply to supply an immense burst of energy. That energy must be maintained in a delicate balance to prevent catastrophic collapse. This balance involves not only counteracting gravitational forces, but also addressing quantum effects that threaten the structural integrity of space-time tunnels. Theoretical physicists have proposed forms of exotic matter with negative energy density as a potential solution. But such matter remains purely hypothetical and unobserved in practical settings. Moreover, even if such matter existed, controlling or producing it in sufficient quantities presents a technological challenge that borders on the insurmountable. These considerations underscore a fundamental tension in physics: the interplay between what may be theoretically possible within Einstein's equations and what is feasible within the energetic and material confines of our universe. This tension ultimately informs why time travel, while tantalizing in theory, remains elusive in practice. Each step deeper into this inquiry reveals the intricate dance between energy, matter, and the unyielding structure of time. It is also important to recognize that the directionality of time, often called the arrow of time, is intimately connected to thermodynamics, particularly the increase of entropy. This natural progression towards disorder provides a macroscopic explanation for why time flows forward and not backward. Any attempt to reverse time would require not only overcoming the enormous energy barriers, but also to locally reduce entropy in a way that violates the second law of thermodynamics. Such a reversal would imply a fundamental disruption to causality, the principle that cause precedes effect, which underpins the consistency of physical laws and the coherence of experience. Without causality, the logical structure of events unravels, leading to paradoxes and contradictions. Consequently, the universe appears to enforce a one-way street for time, rooted in both energetic demands and the preservation of order. These intertwined constraints form a formidable barrier, ensuring that while we may imagine revisiting the past, the physics of our cosmos firmly anchors us to a forward-moving timeline. This understanding deepens our appreciation for the subtle harmony that governs temporal progression. The implications of these energy requirements extend into broader philosophical and scientific reflections on our place within time. Time, as experienced, is not merely a passive backdrop, but a dynamic dimension shaped by the interplay of energy and matter. Our inability to reverse time, in a practical sense, speaks to the profound interconnectedness of physical laws that safeguard the consistency of reality. The enormous energy barriers are not just technical obstacles. They represent fundamental aspects of how the universe is structured. These barriers preserve the integrity of cause and effect, maintaining a coherent narrative of existence that unfolds moment by moment. In this light, the quest to understand time travel transcends mere curiosity, inviting us to contemplate the deep principles that govern all change and continuity. As we continue this exploration, the realization of these immense energy demands guides us toward a nuanced understanding of time, not as a malleable dimension to be bent at will, but as a steadfast flow shaped by the very fabric of reality itself. Such reflections prepare us to venture further into the intricate tapestry of time and its unyielding march forward. At the very foundations of modern physics, quantum mechanics offers a fascinating, albeit complex, perspective on the nature of time. Unlike classical physics, where time is often treated as an absolute and continuous backdrop, quantum theory invites us to consider time as something more subtle and intertwined with the probabilistic behavior of particles and energy states. In quantum systems, events do not unfold in a strictly deterministic sequence, but rather in terms of probabilities that only become definite upon observation. This inherent uncertainty adds a layer of complexity to our understanding of temporal flow. Yet even within this quantum realm, the arrow of time, the consistent forward movement from past to future, remains intact. The laws governing quantum mechanics, while allowing for strange phenomena such as entanglement and superposition, do not permit a reversal of cause and effect in a way that would enable us to travel backward through time. Instead, quantum theory complements the classical view by highlighting that time's forward progression is deeply rooted in the fundamental structure of reality. As we ponder these quantum insights, we begin to see how time, despite its elusive qualities, maintains a steady direction that shapes the unfolding of the universe. One of the key elements reinforcing the forward flow of time in quantum mechanics is the concept of entropy, which measures the degree of disorder within a system. At the quantum level, particles and energy configurations tend to evolve towards states of higher entropy, a process closely linked to the second law of thermodynamics. This natural tendency toward increasing disorder defines a temporal asymmetry, effectively distinguishing past from future. Even as quantum states fluctuate and interact in ways that defy classical intuition, the overall trend toward higher entropy preserves a unidirectional timeline. Attempts to reverse this flow would require an impossible decrease in entropy, demanding energy inputs so vast they exceed the capacity of any physical system. Thus, quantum theory not only accommodates, but also reinforces the arrow of time, ensuring that cause precedes effect and that the past remains fixed as the foundation upon which the future builds. In this way, the quantum world remains consistent with our everyday experience, where time flows inexorably forward, preventing any practical mechanism for traveling backward. Moreover, quantum mechanics challenges us to rethink the continuity of time itself. Some interpretations suggest that time may not be a smooth, flowing river, but a series of discrete moments or quantum ticks. This discretization hints at a granularity in time's fabric, where each instant represents a fundamental quantum event. While this idea remains theoretical and subject to ongoing research, it underscores the complexity of time's nature as more than just a uniform dimension. Yet, even with this granular structure, the sequence of these quantum events aligns consistently with the forward passage of time. The probabilistic outcomes of quantum processes do not imply a reversal of temporal order, but rather a nuanced unfolding of possibilities that resolve into a coherent, forward-moving reality. Consequently, the quantum framework, despite its radical departure from classical views, continues to uphold the principle that time moves in one direction. This subtle interplay between uncertainty and directionality enriches our understanding of why reversing time remains beyond reach. Such insights prepare us to delve deeper into the mysteries surrounding time's irreversible journey. The block universe theory offers a profound perspective on the nature of time, suggesting that past, present, and future all exist simultaneously within a four-dimensional space-time continuum. Instead of viewing time as a flowing river that carries us irreversibly from moment to moment, this theory invites us to imagine time as a vast landscape where every instant, whether it belongs to the past, the present, or the future, is equally real and fixed. In this framework, time does not pass in the way we commonly experience it. Rather, it is laid out like a complete map with all events embedded within it. Our conscious experience of moving from one moment to the next arises from the way our minds navigate this timeless structure. This idea challenges our intuitive sense of time's flow, but aligns closely with the equations of Einstein's theory of relativity, where space and time are intertwined into a single fabric. The block universe thus reshapes our understanding of temporal passage by emphasizing the coexistence of all points in time, rather than privileging the present moment alone. This perspective lays the groundwork for reconsidering why moving backward in time is not just difficult, but fundamentally inconsistent with the nature of the universe. Within the block universe, the concept of causality, the relationship between cause and effect, remains intact, yet is experienced differently than in our everyday perception. In this timeless framework, causes and effects are embedded together in the fabric of space-time, forming a consistent sequence that does not allow for contradictions or loops that would permit time travel to the past. The structure of this four-dimensional space-time is such that each event has a definite position relative to all others, and the order of these events is fixed. Attempting to alter the past would imply changing the fabric itself, creating paradoxes that challenge the logical coherence of the universe. This is often illustrated through thought experiments, like the grandfather paradox, where traveling back in time could lead to contradictions that undermine the very possibility of such journeys. The block universe, by portraying time as a static whole rather than a dynamic flow, implies that the past is as immutable as the future is predetermined. This immutability asserts a fundamental asymmetry in how time operates, one that forbids us from stepping backward through moments already embedded in the structure of space-time. Such reasoning helps explain why, despite the imagination and speculation surrounding time travel, physical laws do not support a return to previous moments. The block universe theory also intersects with concepts from relativity, where observers moving at different velocities perceive time differently, yet all agree on the underlying structure of space-time. This relativity of simultaneity means that what one observer calls now may differ from another's now, depending on their state of motion. Despite this, each observer's timeline remains a continuous thread through the four-dimensional block, unbroken and fixed. This reinforces the idea that all events, past, present, and future, exist together, independent of the observer's perspective. The flow of time then emerges as a subjective experience rather than an objective feature of reality. Our consciousness moves along our personal world line within the block, creating the sensation of time passing. However, physical reality itself does not privilege any particular moment as more real than another. This insight further supports the notion that time travel to the past is prohibited, not by technological limitations alone, but by the very geometry of space-time that defines the universe's structure. Appreciating this subtle interplay between perception and reality deepens our understanding of why time's arrow points inevitably forward. Moreover, the block universe theory invites contemplation of entropy and the second law of thermodynamics, which introduce a directionality or arrow of time within this timeless framework. Although all moments coexist in the block, the increase of entropy, disorder in the universe, distinguishes past from future by marking a progression from lower to higher entropy states. This thermodynamic arrow is responsible for the irreversible processes we observe, such as aging, decay, and the flow of heat, which give us a practical experience of time moving forward. Even within a static block, this gradient of entropy creates a meaningful sequence of events, preserving causality and preventing the reversal of time's course. It is this entropic asymmetry, embedded in the structure of the universe, that explains why we remember the past but not the future, and why actions influence outcomes in a one-way fashion. Consequently, while the block universe posits a timeless reality, the physical laws governing entropy ensure that our experience of time remains unidirectional and consistent with everyday observations. This connection between timelessness and thermodynamic order further illuminates the reasons we cannot physically return to moments that have already unfolded. The experience of the present moment is deeply intertwined with the nature of consciousness and perception, which serve as the bridge between the physical passage of time and our subjective awareness. While physics describes time as a dimension much like space, our conscious minds do not perceive time as a static landscape, but rather as a flowing current. This flow arises because consciousness processes sensory inputs sequentially, constructing a continuous narrative from discrete moments. The brain integrates signals over brief intervals, creating what we recognize as the now, a fleeting window where past memories and anticipations of the future converge. In this way, the present moment is not simply a point on a timeline, but an emergent property of how our minds interpret and organize temporal information. Our perception is thus inherently tied to this ongoing synthesis of experience, anchoring us in a temporal reality that feels immediate and dynamic, even if the underlying physics suggests a more complex structure. Furthermore, the neurological mechanisms that underpin consciousness are intimately connected to the brain's capacity to process cause and effect, reinforcing the directionality of time as we experience it. Neurons communicate through electrical and chemical signals that unfold in a specific order, reflecting the irreversible sequence of events dictated by the universe's entropic progression. This ordered chain of neural activity supports the formation of memories and the anticipation of future outcomes, both essential to survival and decision-making. Because our brains are shaped to respond to temporal asymmetry, we find it natural to move forward in time, perceiving the present as a unique and unrepeatable moment. Attempts to revisit the past conflict with this fundamental neurophysiological framework, as memory is reconstructive rather than a perfect replay, and the physical conditions that constituted previous moments no longer exist in the same configuration. Thus, consciousness itself encodes the unidirectional flow of time, aligning our subjective experience with the physical laws that govern temporal progression. In addition to consciousness, perception relies on the interaction of sensory systems with the environment, which is subject to irreversible changes dictated by thermodynamics. Light, sound, and other stimuli arrive at our senses in a sequence that mirrors the increasing entropy of the universe. This means that the information reaching our brain is always moving forward through time, shaped by ongoing transformations in the physical world. Because these sensory inputs cannot be reversed or undone, our perception is locked into a forward-moving stream, reinforcing the impossibility of physically revisiting earlier states. The universe's relentless march toward disorder ensures that every present moment is distinct and non-reproducible, a unique confluence of energy and matter that continuously evolves. Our sensory experience, therefore, is a reflection of this universal temporal asymmetry, grounding our sense of now in a reality that is both physically and perceptually irretrievable once past. This intimate link between perception and entropy further clarifies why time travel to the past remains beyond our reach. Moreover, the subjective sense of the present is supported by the brain's temporal binding processes, which integrate events occurring within milliseconds into a cohesive experience. This binding creates a temporal horizon that defines what is perceived as simultaneous and what is understood as preceding or following. The brain's temporal resolution, though limited, is finely tuned to different sensory modalities, allowing for a seamless flow of experiences that constitute our conscious awareness. Because this process depends on ongoing physiological activity that cannot be reversed, our conscious experience is perpetually anchored in the present, constantly updating with new information while letting go of what has already passed. This dynamic updating is essential for interacting with a world that itself moves irreversibly forward in time. It also explains why the past exists only as memory and the future as anticipation, with the present serving as the ever-changing boundary between these two temporal realms. The brain's temporal architecture thus enforces a directional experience of time that aligns with the universe's physical constraints. Ultimately, the intertwining of physical time, entropy, and conscious perception forms the foundation for why we experience time as a continuous progression rather than a static block. While the laws of physics describe time symmetrically at fundamental levels, the emergent properties of complex systems like the brain and the irreversible increase of entropy create an effective arrow of time that structures our lived experience. This arrow not only shapes how we perceive moments, but also imposes strict limitations on our ability to revisit or alter the past. Our present consciousness is a product of these intricate relationships, a living narrative unfolding within a universe that moves inexorably forward. As science continues to deepen its understanding of time and mind, it reveals the profound connection between the cosmos and our personal experience, highlighting why the present moment is both all we truly know and all we can ever inhabit. This perspective opens the path toward exploring how consciousness and time coexist, setting the stage for further reflection on the nature of temporal experience. Memory serves as the intimate thread that weaves our conscious experience into the fabric of time, anchoring us firmly in the present moment while simultaneously reaching back into the past. Our brains do not merely record events like a passive camera. Instead, they actively reconstruct and interpret memories, creating a dynamic tapestry that shapes our sense of identity and continuity. This process is inherently directional, reflecting the one-way flow of time as it unfolds. Memories accumulate in a linear sequence, building upon what has already occurred, but never allowing for a true retreat. This directional quantity of memory parallels the physical arrow of time, dictated by entropy, binding us to the present and making the past a fixed, inaccessible domain. The mind's reliance on memory to navigate time means that, while we can recall and relive past experiences internally, these moments exist only as representations, not as physical realities we can re-enter or alter. Our psychological connection to time, therefore, is inseparable from the workings of memory, reinforcing a profound truth. Although the past shapes who we are, it remains forever out of reach in the tangible world. The laws of physics, particularly those related to thermodynamics, underscore why the past is locked away from our physical grasp. Entropy, the measure of disorder in a system, tends to increase over time, giving rise to an irreversible progression from order to chaos. This irreversible trend is not just a theoretical abstraction, but a fundamental feature of the universe that dictates the flow of time as we experience it. Memory itself is a product of physical processes in the brain, which emerge and evolve within this entropic framework. Once an event has passed, the energy states and information patterns associated with it inevitably transform, precluding any exact recreation or return to that moment. Attempts to go back would mean reversing countless microscopic processes, a feat that contradicts the very nature of entropy and the second law of thermodynamics. Thus, the arrow of time becomes embedded not only in the cosmos, but also within our neural architecture, making physical time travel to the past an impossibility, grounded in the fundamental rules that govern reality. This intimate link between memory, entropy, and time's directionality reveals why our experience of the past remains a narrative rather than a destination. Beyond the physical and biological constraints, the phenomenology of memory highlights the subtle ways in which our perception of time is constructed and limited. Memories are inherently selective, often fragmentary, and subject to change with each act of recall, illustrating that the past is not a static archive, but a living aspect of our consciousness. This fluidity underscores the distinction between experiencing time as a flowing continuity and the impossibility of physically revisiting past events. Each remembered moment is filtered through layers of interpretation, emotion, and context, which evolve alongside our ongoing experience. In this way, memory serves both as a bridge to what has been and a reminder of what can never be physically restored or relived. The past exists in our minds as a mosaic of impressions, rather than a place to which we can return, emphasizing that the temporal journey is one way, shaped by the interplay between neural processes and the irreversible march of time. Our awareness of this boundary invites contemplation on how consciousness navigates the river of time, tethered always to the here and now. The intertwining of memory and time also reveals the profound human experience of longing and nostalgia, emotions rooted in the awareness of time's unidirectional flow. This emotional dimension arises precisely because we recognize that the past, while accessible through memory, is fundamentally unreachable in its original form. Our memories, vivid or faint, create a sense of presence for moments long gone, yet they simultaneously affirm the impossibility of physical return. This tension between remembrance and loss shapes much of our inner life, coloring how we relate to ourselves and the world around us. It is this delicate balance that deepens our appreciation of the present moment, the only slice of time where memory and reality converge. In this way, memory not only anchors us in time, but also enriches our experience of temporal existence, framing the continuous unfolding of life within the constraints of what can be known and what must remain forever beyond reach. As we reflect on these truths, we prepare to explore further how consciousness and temporal awareness intertwine to define the human experience. Time, as experienced through biological processes, unfolds in a single, unyielding direction. Unlike many physical phenomena that can, in theory, be reversed or replayed under controlled conditions, living systems operate with an inherent temporal asymmetry. At the heart of this asymmetry is the concept of entropy, a measure of disorder that invariably increases over time in closed systems. In biology, this manifests as the gradual, irreversible progression from youth to old age, a visible and tangible marker of time's arrow. Cells divide, differentiate, and eventually deteriorate. Molecular structures accumulate damage that cannot be perfectly undone. This progression is not merely a metaphor, but a fundamental characteristic of life itself, where the sequence of events builds upon what has come before, never retracing its steps backward. This forward march is evident in every heartbeat, every breath, and every moment of growth or decline, reinforcing the reality that biological time cannot be rewound or paused, only lived through. The aging process exemplifies time's irreversibility in a way that is both subtle and profound. As cells undergo countless cycles of replication and repair, molecular errors accumulate, leading to gradual functional decline. Telomeres, protective caps at the ends of chromosomes, shorten with each division, signaling a biological clock that counts down rather than resets. This cellular senescence contributes to the gradual transformation of the organism, a journey from vitality toward fragility. Unlike mechanical clocks, which can be reset, or digital files that can be restored to previous versions, biological systems do not possess a mechanism to reverse this cellular aging naturally. The flow of time in living organisms is a one-way stream, shaped by biochemical pathways that favor forward progression, reflecting the thermodynamic realities that govern all matter. We observe this in the fading strength of muscles, the slowing of metabolic processes, and the subtle shifts in cognitive function, each a testament to the inexorable passage of biological time.
At a molecular level, the irreversibility of time is underscored by the complex interplay of chemical reactions that sustain life. Enzymatic processes, energy transfers, and genetic expressions all proceed in sequences that are finely tuned to move forward. The second law of thermodynamics ensures that these reactions produce byproducts and changes that cannot be simply undone. For instance, oxidative stress results in damage to proteins and DNA, accumulating over an organism's lifespan and contributing to aging and disease. Repair mechanisms exist, yet they are imperfect and cannot fully restore original conditions. This molecular asymmetry parallels the larger biological narrative, reinforcing the concept that time's arrow is embedded deeply within life's very fabric. Consequently, our bodies are not static archives but living chronicles, continuously shaped by time's forward flow and the inevitability of change it brings. The unidirectional nature of time in biology also shapes how we perceive life and mortality. Our awareness of aging and the finite span of existence imbues each moment with significance, underscoring the preciousness of the present. The inability to reverse time biologically means that experiences once past remain forever part of our personal history, influencing our physical form and mental state. This realization connects deeply with our earlier reflections on memory and the impossibility of returning to the past. It is an intimate dance between time's progression and the living body that defines much of our human condition. In this light, the constant forward movement of biological time is not simply a constraint, but a framework within which life's richness unfolds, shaped by growth, change, and eventual transformation. Understanding the irreversibility of biological time invites us to consider the broader interplay between consciousness and temporal awareness. As living beings, we not only experience time through physical changes, but also interpret its passage through cognition and emotion. This dual awareness, the physical aging of the body and the mental reflection on time's flow, creates a profound connection to the present moment. It is within this space that life is both lived and understood, framed by the unyielding direction of time itself. Our journey forward continues, shaped by these biological and experiential realities as we prepare to explore the deeper dimensions of consciousness and temporal perception. While physical time flows steadily and uniformly through the cosmos, measured by the rhythms of planets, atoms, and light itself, the experience of time within our minds unfolds quite differently. This distinction between psychological time, the subjective feeling of time passing, and physical time, the objective, measurable progression of moments, helps to clarify why certain experiences can feel swift or sluggish, despite the clock ticking at a constant rate. Our consciousness creates a temporal landscape colored by attention, emotion, and memory,
which can stretch or compress the perception of a single minute or hour. For example, moments of joy or intense focus may seem to fly by, while periods of boredom or waiting feel protracted and heavy. This disparity arises because the brain does not simply register time like a stopwatch. Instead, it interprets and constructs the flow of time based on internal states and external stimuli. The interplay between these two forms of time reveals how deeply personal and malleable our experience of the temporal world truly is. Physical time, as described by physics, marches forward in a linear, unidirectional fashion, governed by the fundamental laws of thermodynamics and causality. This arrow of time is intimately tied to entropy, the gradual increase in disorder, which prevents processes from spontaneously reversing. Within this framework, the past is fixed and immutable, the present is fleeting, and the future remains uncertain and open to possibilities. This asymmetry is why, despite countless stories and theories, traveling backward in time remains a concept confined to imagination and theoretical speculation, rather than reality. The universe's physical laws impose strict constraints, ensuring that cause precedes effect and that events unfold in a sequence that cannot be undone. Thus, while our minds may wander backward in memory or leap forward in anticipation, the physical fabric of time itself remains relentlessly forward-moving. The inability to reverse physical time also underpins the fundamental difference between remembering and reliving. Psychological time allows us to revisit moments in our minds, drawing upon stored memories to reconstruct past experiences. However, this mental journey is not equivalent to physically re-experiencing those moments. The brain's capacity to simulate past events or imagine future ones enriches our understanding of time's passage, but does not alter the irreversible progression of physical events. Our memories are filtered through perception and emotion, often reshaped by reinterpretation, which further separates subjective time from the objective timeline. This distinction underscores why the feeling of nostalgia or regret, while powerful, cannot translate into actual temporal reversal. Instead, these experiences deepen our appreciation of time's flow and the unique nature of each present instant. Moreover, neuroscience suggests that the brain's internal clocks and timing mechanisms contribute significantly to how we perceive time's passage. Neural circuits synchronize to encode sequences of events, durations, and rhythms, creating a coherent sense of temporal continuity. Disruptions to these processes, whether through altered states of consciousness or neurological conditions, can distort psychological time, making minutes feel like hours, or vice versa. This intimate connection between brain function and temporal experience reveals how subjective time is crafted within the mind, distinct from the steady ticking of physical clocks. Understanding this dynamic offers insight into why time can sometimes seem elastic, bending to the contours of our mental and emotional states, even as the external world remains constant. This exploration of psychological versus physical time invites us to appreciate the complex relationship between the mind and the universe's temporal fabric. While physical time provides the framework within which all events occur, our psychological experience colors this framework with depth and meaning, recognizing that moments feel different, not because the clock changes, but because our consciousness shapes our experience, opens a window into the rich tapestry of human awareness. As we continue to delve deeper into the mysteries of time, we begin to glimpse the profound ways in which consciousness and reality intertwine, preparing us to explore the deeper dimensions of temporal perception and the nature of now. Throughout human history, the concept of time travel has captured our imagination, weaving itself into countless stories, myths, and works of fiction. These narratives often reflect a deep-seated desire to revisit the past, to undo mistakes, or to glimpse futures yet to come. In popular culture, time travel is frequently portrayed as a tantalizing possibility, a way to rewrite history or alter the course of events. Yet, these stories also reveal underlying anxieties about the consequences of such power, cautioning that tampering with time could unravel the delicate fabric of reality. By examining these myths and fictional explorations, we gain insight into the hopes and fears that shape our collective understanding of time itself. We see that time travel is not merely a plot device, but a mirror reflecting profound human concerns about causality, choice, and the irreversible flow of existence. From a scientific perspective, however, the idea of moving backward through time encounters significant challenges grounded in the fundamental laws of physics. Time, as understood in the framework of modern physics, is intimately connected to the second law of thermodynamics, which dictates that entropy, or disorder, increases over time. This increase creates an arrow of time, a directionality from past to future that is deeply embedded in the structure of the universe. While certain equations in physics are time-symmetric, allowing processes to run forward or backward, the macroscopic experience of time is unidirectional. This asymmetry suggests that while moving forward in time aligns with the natural order, reversing that flow contradicts the fundamental progression toward greater entropy. These scientific principles highlight why time travel to the past, as imagined in stories, remains beyond our current understanding and technological reach. Moreover, the concept of causality, the relationship between cause and effect, presents additional barriers to backward time travel. In our everyday experience, causes precede effects, creating a logical sequence that underpins reality and decision-making. If one were to travel back in time and alter past events, this sequence could be disrupted, potentially leading to paradoxes such as the famous grandfather paradox, where a traveler might prevent their own existence. Such contradictions challenge the consistency of physical laws and raise profound questions about the nature of reality itself. Although some theoretical models, such as those involving wormholes or parallel universes, propose mechanisms that might circumvent these paradoxes, they remain speculative and unproven. The persistent difficulty in reconciling backward time travel with causality underscores the complexity of temporal mechanics and the subtle interdependence of time and reality.
In addition to scientific constraints, our psychological experience of time also shapes how we perceive the possibility of traveling through it. Human consciousness is inherently anchored in the present moment, with memories extending backward and anticipation reaching forward. This flow creates a sense of continuity and identity, making the idea of revisiting past moments both intriguing and unsettling. The narratives of time travel in popular culture often explore these psychological dimensions, reflecting desires to heal regrets or relive joyous experiences. At the same time, they expose fears of losing control or facing unintended consequences. These stories serve as a canvas upon which we project our complex emotions about time, its passage, its meaning, and the limits it imposes on our lives. As we continue to explore the interplay between the scientific realities of time and the rich tapestry of human imagination, we begin to appreciate why time travel remains a powerful symbol rather than an achievable feat. The enduring fascination with reversing time speaks to a fundamental human longing to understand and, perhaps, transcend the boundaries of our existence. In contemplating these myths and scientific insights, we open a pathway toward deeper questions about the nature of time, consciousness, and the universe itself. This reflection prepares us to further investigate the nuances of temporal perception and the meaning of the present moment, inviting us to embrace the mysteries that time continues to offer.